All right, hi everybody. This is a video on using equilibrium constants. We introduced all of these topics last week. I just want to point out that for today's video, the goal is going to be to go through and do a few problems using those ICE tables that we've introduced in the past. So that is going to be one of the highlights of this particular video. The first question we are given actually runs through the conversion from equilibrium constants in terms of pressures to equilibrium constants in terms of concentrations. Remember that in order to do this, we need to know temperature and we need to have some kind of an equation to find a change in number of moles that are in play. So for this first reaction, we're actually given a Kp, we're given a temperature in Kelvin, so that's really nice, and we have an entire reaction that we can use to determine delta N. And when we want to determine delta anything, remember it means final minus initial. In the case of a chemical reaction, final is products and initial is reactants. So for delta N for this, there's a 1 in front of our products, and then there is a 1/2 and another 1 in front of our reactants. When we do the math here, we end up with a -1/2 as our delta N value. Okay, just kind of setting us up for part A. So part A is asking us to calculate Kc. What is that going to be? In order to do this, we need Kp, we were given it to be 1.85. We need T, we were told it's 1,000 Kelvin. We need our delta N, we just calculated it to be -1/2. We need R, in this case, R is back to the original gas constant unit, liters ATM per mole Kelvin, because we want our K value to match the units we've already used. Okay, plugging all of that in. Remember, we're going to be using this equation, so we may want to rearrange it to get RT delta N to the other side. In order to do that, we get this equation. Okay. Oopsies. Hold on. Be patient with me. Oof. Navigating a tablet. So fun. Alright. Alright. So Kc equals there's 6 times 1,000. Remember, it's this term that gets raised to the -1/2 power. So in our calculators, you may need multiple parentheses, but you should be able to do this one in your calculator, no problem. I'm going to pause my video real quick while I do this math. All right, in my calculator, I ended up with a value of 16.76. There is no unit on that one, but that answers question or part A of our problem. Looking at part B, oh my gosh, the view of this was just not, here we go. All right, so part B says, what is the value of Kp for the reaction if it has double the quantities as it did in the first part? And in order to remember this, you're going to have to remember our rules on what happens if we manipulate equations, what happens to our K values. So just a reminder, that when we change our reaction coefficients, so if, for instance, we double them, then we want to square or use whatever factor it is to get our new coefficient. So for this one, because we doubled every coefficient, oh, it actually wants Kp, so we're going to square Kp, not Kc. My apologies. Kp if doubled reaction stoichiometry. So we're going to do Kp squared, should be 1.85 squared, which in my calculator comes out to be 3.42. For part C, I'm going to let you guys do that one, and I want to see your answers. So essentially what I want you to do is do part C on your own. So when you turn in your notes of this video, you'll also do this one on your own. It wants you to calculate Kc given the new Kp. Remember, use the same conditions. You're still in, you're still at 1,000 Kelvin, et cetera, et cetera. All right, problem number 2. We are going to use some information about our ice tables in order to actually determine what we need to know. So we're told to calculate a Kc. So that's the first thing I want to make sure you guys see in the problem. Okay, calculate a Kc. What that means is that we are going to have to actually set up what a Kc is going to look like. Remember that we're going to use our balanced chemical equation given there. It tells us that methanol, CH3OH, is formed from carbon monoxide and hydrogen gas. And when it's formed, it requires 2 equivalents of the H2 gas in order to do so. One of the things to notice about our equation is that there are no liquids or solids, so everything is in play. So I'm going to start this problem by writing a K expression. Anytime we're doing these types of problems and we know that we're probably going to be doing something with equilibrium, I like to start with an equilibrium expression because it's one of the easiest habits for us to get into. Write the K expression, see what happens. Okay, so now we have a K expression. We were also given some information about an equilibrium mixture, which means we're already at equilibrium. Now remember that Kc requires our stuff in moles per liter. So all of these molar amounts we're told that exist at equilibrium, we have to convert to molarities by dividing by our volume of 2 liters. So I'm going to go through and I'm going to do that first. So I'm going to take my concentration of CH3OH, which I'm told is 0.0406 moles in 2 liters. I'm going to do the same thing for the other 2, my CO. Oops. 0.302 moles in 2 liters. Oops, not moles. And then my concentration of my H2 was found to be 0.302 moles in 2 liters as well. Oops, I think I screwed this one up. I'm going to change that. 170 moles in 2 liters. Okay. Tossing those in a calculator for me. And notice that the equation we are doing, just as we're doing our problems here, notice that it doesn't require at any point am I asking about a temperature. Okay, the temperature tells us that this equation or that this reaction has already happened, which means we don't necessarily have to do anything to make it work, as far as we don't have to take that temperature into account. Okay, we just need to know that it is at that temperature just in case we're asked something in the future. Now this question only has one part, so I'm not going to ask that we go through and do anything on our own in this particular case, but I do want to make sure that we all understand the process of calculating a K given specific information. And you may have to do the same thing where I'm given a mole and I needed to get to molarity, so I'm dividing by the volume. You may be given moles and asked to find pressures, and remember that when we're asked to find pressures, we have to use the ideal gas equation. So depending on what you're given is what's going to determine how you find your answers. Just remember that Kc's must be in moles per liters and Kp's must be in terms of pressures. And when we say pressures, usually we mean ATM, okay? Because the R equation, or the R constant, gas constant, is always usually in terms of ATM. It's the universal unit, if you will. Okay, all right, so from here, then we're going to take all of these values and we're just going to plug them in to the Kc expression. I apologize for the jolting transition there. I know that that's kind of annoying. My typical device, I'm having some trouble today, so please be patient. Our Kc is going to be our 0.0203 over 151 squared because it's H2. Kc is going to come out to be 5.24 is the value I got for that particular reaction. Okay, so here's our next problem. And this one we are actually going to have to make an ice table. So knowing that, and because I am familiar with them, even if you don't know that, remember that one of the things we can always start with is a K expression. So we are given a value of, we are given the equation to do so. In writing this, remember to follow your rules. All of them are gases, so they're all going to participate. But remember that, for instance, like H2O, since it has a 2 in front of it, remember products over reactants, the coefficients become the exponents that we raise our concentrations to. In this case, we're also going to do H2 on the bottom, raised to the power of 2 because of the coefficient, times NO, again, raised to the power of 2, coefficient. So now we have a K expression at the very least, okay? Next thing I'm going to do is I'm going to read and try to understand what I'm being asked. I'm told that a sample of NO gas and a sample of H2 gas and a sample of H2O is placed in a vessel at 300 K, and then equilibrium is established. So knowing that it says the following equilibrium is then established, aka comes after I've charged it with these initial amounts, I know that these are initial amounts because it didn't say at equilibrium here are the concentrations. I also know because the first thing that we're going to solve together is to calculate the equilibrium concentrations of everything that are in this particular reaction. Okay, I'm already given one equilibrium concentration as well, so we're going to come back to that after we set up our ice table. In order to set up an ice table, I usually just write the reaction again. So that I can write underneath the reaction, because that's where I'm actually going to put my ICE. Okay, I'm told I started with 0.1 moles. I also know that if I have to use a Kc at some point in this particular reaction, and I know I was given a concentration at equilibrium, that I should probably convert all of these molar amounts to molarities like it's expected in the actual process. Now, luckily, all of this is in a 1 liter vessel. So if I divide everything by 1, they stay in their same amounts. So for instance, 0.1 moles of NO still is 0.10 molar of the NO. Okay, from there, I'm just I'm gonna put stuff into my ice table like we did in class last week. I'm gonna make sure that I've put everything that I know belongs in their specific locations. So if I'm not given an amount, like for N2, I know I started with none of this, which means that by definition, we must be subtracting from the left side to create the right side. Just because these are reactants and these are products doesn't mean that all equilibriums will move in a forward direction. That's not the way this is, and that's something really important for us to remember. They can go both ways, so we always want to analyze and see which direction makes the most sense. We know that, for instance, we can't remove anything from the product side and make reactants because there is no product N2 to work in that particular method. In order for for concentrations to decrease, they would have to go, you'd have to have some of each in order to make it work, is what I'm trying to say. Okay. I'm also told that at equilibrium, the NO concentration is 0.062 molar. I don't know anything else. I can calculate what this change in concentration is. From our discussions in class last week, remember, again, we're going to be subtracting, and because there's a 2 in my reaction, we're going to be subtracting 2 equivalents of whatever we are subtracting. Over here, if you look at H2, we're also going to be subtracting 2 of that here. And on the right side, we know we're going to be adding 1 equivalent to N2. I know I'm going to be adding 2 equivalents to my H2O. Okay, so there's some information for me to fill in that change column based on what I understand is going to happen in a reaction. And for us, we are not actually plugging in this information to like calculate, like we're not doing the quadratic or anything. This is actually just really straightforward, like algebraic manipulation. If I'm going to subtract 2x here and I know what I'm going to end with, I can calculate what x is by just setting up an equation. For instance, I know, sorry, my pen, I know this must be the case based on the information I was given in this problem. So I can subtract, I can do negative 2x equals negative, hold on, my brain isn't working. Sorry, so I skipped ahead a little bit. My filming device is not participating. So I skipped ahead a little bit. We're dividing both sides by 2, and we're going to get that x equals, oops, sorry, you're dividing by negative 2, so the negatives cancel. What are we going to get? Negative 0.38 divided by 2. Dum-dum. Where are my math people when I need them? Sorry. I got 0.019. Okay. And remember that when we're doing this particular type of manipulation, this has to make sense mathematically. So when I subtract 2 equivalents of the 0.019, aka the 0.038, from the H2 concentration up here that I started with, it has to leave something behind or not go below 0. So subtracting gives me 0.012. Remember, now I'm plugging that x in to my equilibrium table to get these values at equilibrium, because my first question was, what are all the equilibrium concentrations? I know this is just 0.19. I know that this is 0.138. Remember, they are all in terms of molarities at this point. From there, part B of this question says, what is Kc? And again, I'm going to let you guys do that problem on your own. All right, last problem. Again, I'm given some information about moles of things. I am going to let you make an attempt on this problem on your own. This video is already at 18 minutes. I did not want to go beyond 20. So I know you have double period on Thursday and Tuesdays, right? So I will film this for another class, but for now, I think I'm going to pause. I want you to finish the 2 problems I gave you in this video, plus I want you to make sure you're understanding what's happening, and then I want you to make an attempt on this problem on your own, knowing that you're given moles, okay? You're given moles, you're given volume, you're given a temperature. Remember, PV equals nRT. Remember, R is 0.08206. Okay, you have all of the information you need at your fingertips to convert your moles to pressures. Once you have everything in pressures, you set up an ICE table and try to get those initial values, because these are all initials, to get to equilibrium. And you're given one equilibrium concentration or pressure, just like you were in the previous problem. So we're just kind of taking a different approach to this problem. And then the last 2 parts of this problem are actually asking you to do Kp and Kc. I will work out a solution and put an answer key up tomorrow so that you can see how this problem is answered. You will also spend a bunch of time tomorrow and or the next class period that you're working on this, working on equilibrium problems. So just work hard to understand what's happening in here and try really hard to do this problem on your own. I really do think you can do it. You just have to put the information in an organized manner. Okay? All right. Thank you very much.